Hey there. So today we are going to be looking at this question which I made myself, and the question is as follows. So let Sn be this set from of the natural numbers from 1 to n, and define a switch to be the act of exchanging any two adjacent elements from in any given permutation, and let f of n be the least number of switches required to cover all permutations of Sn. So what that basically means is, let's say n is equal to 3. So in that case Sn is 1 to 3, so we start with this permutation, then let's say we switch 2 and 3, so we end up with 1 3 2, then let's say we switch 3 and 1, so we end up with 3 1 2, and let's say we switch 1 and 2, so we end up with 3 2 1, and from there we can get 2 3 1, and from there we can get 2 1 3. So this way we have covered all permutations of S3, because we started off with this, then we ended up at this, and that way we have covered all 6 permutations of S3. So over here we see that f of 3 is equal to 5, because this is the least number of switches required and it's 5. So f of 3 is equal to 5, and that way we define f of n for any general n, and we have to prove this relation for f of n. So firstly, notice that this part is actually unnecessary, because f of n has to be greater than n factorial minus 1, because a switch is basically a transition from one permutation to another permutation, and since we have n factorial total permutations, we'll have to perform at least n factorial minus 1 transitions from one permutation to another to cover all of them. So this part is actually trivial. So the main juice of the question is in proving this part. So this is what we are going to be focusing on. Okay, so now let's get started. So firstly, the method which we are going to be using to solve this question is similar to the method which we use to prove that such a sequence must exist in the first place, which is over on my Instagram page. So it's basically a more efficient algorithm for doing the same task. So what we'll do is, in that proof we started off with 1 2 ... n plus 1. So it was basically a proof by induction. If we can do it for Sn, then we prove that it can also be done for Sn plus 1. So we know that we can cover all possible permutations of these n elements, so we'll do that, and then let's say we end up with some permutation of these, and then n plus 1. So what we did in the method for proving that such a sequence must exist is that then we reversed all these this entire sequence of switches. So we ended up back at this, because any switch can be reversed, and that means any sequence of switches can also be reversed. So we just perform the exact opposite of what we did, and we end up back at this. Then we switch n and n plus 1, and then we end up at 1 2 ... n plus 1, and then n, and then we cover all possible permutations of these n elements, because we can do that by the induction hypothesis, and then again we end up with some permutation sigma, and then n, and then once again we reverse all our switches, and then we switch n minus 1, which is over here, with n plus 1, so that it comes in this place. Then we switch n minus 1 with n to put it in the last place, and then again we perform our sequence of switches to cover all possible permutations of this. So basically the idea is that first we put n plus 1 in the last place, then we put n in the last place, then we put n minus 1 in the last place, and that way we have covered all possibilities, and hence we have proved that such a sequence must exist. So now if we use this same method to find an upper bound for f of n, then notice what we are doing. First we perform f of n switches, then we perform f of n switches once again to bring us back over here, like basically the reverse of the sequence which we performed over here. So we have already performed two times f of n switches, and then we perform one more switch, then again we perform 2 f of n switches, and so on. So that's really inefficient, because if you notice, every time we go ahead we come back, and then we go ahead and come back and go ahead and come back. So that's taking a lot of switches. So we want to be more efficient, and for that, instead of going back, what we'll do is sigma will have some last element, right? Obviously. So let's say the last element is a1, and a1 hasn't been in n plus 1's place so far. So what we can do is we can switch n plus 1 and a1 to end up with stuff, and then n plus 1 a1. Then we perform f of n switches on these n elements to cover all possible permutations of these with a1 in the last place, and then let's say we end up with some new sigma and a1. So now sigma will again have some last element, let's say a2. Now we can switch these, and once again with a2 in the last place we'll cover all possible permutations, except there is a slight mistake in that logic. The mistake is that a2 can also be n plus 1, and if a2 turns out to be n plus 1, you have put n plus 1 back in the last place, and once again you're performing f of n switches to cover permutations which you have already covered. So it's a complete waste of permutations or switches. So what we need to do is we also need to look at the second last element of sigma, which is a3. So in case a2 is not n plus 1, we can just switch a1 and a2, and in case a2 turns out to be n plus 1, which is a bad scenario but it is possible, so we have to cover it, we switch a3 with a2 so that we end up with a2 over here and a3 over here, and then we put a3 over here, and we are guaranteed that a3 won't have been covered previously because the last element has only been n plus 1 or a1, and since we know that a2 is equal to n plus 1 in the worst case scenario, a3 can't be n plus 1, and hence if we put that over here, then we are done. So then let's assume the worst case scenario, then we'll have covered all possible permutations with a3 in the last place. Now once again sigma will have some last elements, let's say b1. So now we can switch a3 and b1, but once again the same problem has happened because b1 can equal n plus 1, in which case we are doomed. b1 can also equal a1, in which case once again we are doomed. So that means we need to go to the next element, let's say b2. Now let's say in the worst case scenario b1 turns out to be n plus 1. So then we look at b2. Well, then we switch b2 and b1 to bring b2 over here, and then we put b2 over here. But once again there can be a problem, because if b1 is equal to n plus 1, there is again a possibility that a1 is equal to b2, and if a1 is equal to b2, once again we are doomed because we are putting an element in the last place which has already been over there. So we may need to look one more element to the left. So let's say b3. So it's getting really unneat, but I hope you get the idea. So b3 is guaranteed to not be n plus 1, or rather I would say that at least one of these three is guaranteed to not be equal to n plus 1 and a1. So that means the worst case scenario is we'll have to perform one switch, then one more switch, and then one more switch, so total 3 switches, and so on. The number of switches in the worst case scenario will keep on increasing, and the worstest case scenario for the last step is n. So what we are basically doing is we performed f of n switches over here, so f of n, and then plus we performed one more switch which was n plus 1 and a1, so plus 1. Then we performed f of n switches again, so plus f of n, and then in the worst case scenario we performed 2 switches, so plus 2, and so on till f of n plus n, and then to end it all we perform f of n switches. So f of n plus 1 is guaranteed to be lesser than or equal to this expression because of all of this. So now that we have found an upper bound for f of n plus 1 in terms of f of n, we can do some manipulation to find a upper bound in terms of n directly and without f of n as a middleman. So let's do that. Okay, so I've cleaned up our inequality over here. So we had n plus 1 f of n's, and then we had 1 plus 2 plus 3 and so on till n, so that combines into n plus 1 by 2. And one thing I noticed is that I made a mistake in the question, and f of n is supposed to be less than or equal to n factorial over into e by 2, so that is actually a better upper bound than before, so that's good. And now what we'll do is we'll define a new sequence g of n, and we'll define it by g of n plus 1 is equal to g of n into n plus 1 plus n plus 1 by 2, and g of 1 is equal to f of 1. So what we have basically done is we have changed this inequality sign into an equality sign, and then we are guaranteed that g of n is greater than or equal to f of n. So if we find an expression for g of n, then we are basically done, because we can put that over here and we have found our upper bound. So now what is f of 1? Well, how many switches do you need to cover the permutations of this set? 0. So this is equal to 0, which is a nice number to deal with. So now what we'll do is we'll find g of n using this expression. So well, notice that we can substitute something over here for g of n in terms of g of n minus 1. So g of n is equal to n g of n minus 1 plus n minus 1 n by 2. So it basically comes from the same relation by replacing n by n minus 1 over here. So we end up with g of n plus 1 is equal to n plus 1 n g of n minus 1 plus n plus 1 by 2 from here, and then plus n plus 1 n minus 1 by 2 from here. So basically this n plus 1 gets multiplied onto this, and now we have found this expression. And well, we can keep going, and if you notice the pattern, this is basically n plus 1 factorial over n minus 1 factorial. So in the general case, when we write this as something into g of 1 plus something, then this something will actually be n plus 1 factorial over 1 factorial, because this is n minus 1 factorial. So over here, if we put 1, we get 1 factorial. So now what I'll do is I'll take this half factor common, so we get half n plus 1 n, and then plus n plus 1. So once again, if you write it in this form, this is basically n plus 1 factorial over n minus 2 factorial. And since if we put n minus 1 over here, we are getting n minus 2 factorial in the last term. So if we put 1 over here, we'll get 0 factorial in the last term. So on till n plus 1 factorial over 0 factorial. And this is n plus 1 factorial over n minus 1 factorial. So now what we'll do is we'll take n plus 1 factorial common, and g of 1 is equal to 0. Where was that? Yeah, over here. So this is basically negligible, and then we get half n plus 1 factorial times 1 over 0 factorial. So I'm starting from this end, then 1 over 1 factorial, and so on till 1 over n minus 1 factorial. And now notice that this is just the Taylor, like a partial sum of the Taylor series of E. So this is less than or equal to E. So f of n plus 1 is less than or equal to E by 2 times n plus 1 factorial. So we get f of n is less than or equal to E over 2 n factorial, and we have proved our claim. And actually this, if we just put this over here in place of E, then our approximation will be better, because this is lesser than or equal to E. But if you do that, the answer will be pretty ugly, and the answer will actually also give a hint to how the question is to be solved. So that's why I put E over here, because it looks much better and the question looks much more intimidating. So I hope you enjoyed, and if you like this, then you'll certainly like the Instagram posts which I made. You can find them in the description, and thanks for watching.
Thank you for watching.